Let's take this gate question. The state of stress at a point for a body in plane stress is shown in the figure below. If the minimum principal stress is 10 kilopascals, then the normal stress sigma y in kilopascals is, so sigma x is given 100 kilopascals, tau xy is given 50 kilopascals. Data is available on Mohr circle in the problem. Sigma x is given 100 and tau xy is given 50. So the coordinate of point A will be 100 and 50. Center is sigma average, that is average of sigma x and y, and 0. Sigma min or sigma 2 is given 10. So the coordinate of the point, say n, is 10, 0. Let center be C. So NC and CA both are radius. So we can write NC square is equal to CA square. NC will be sigma A minus 10 whole square, and CA will be equal to 100 minus sigma A whole square plus tau xy whole square. Opening the brackets and putting value for tau xy, we have sigma A square plus minus 20 sigma A plus 100 is equal to 10,000 minus 200 sigma A plus sigma A square plus 50 square. Sigma A square cancels. Solving for sigma A, we get the value of sigma A is equal to 68.88. Now we have sigma x plus sigma y by 2 is equal to 68.88. We get value of sigma y is equal to 37.78. So the answer is 37.78. Let's solve another gate question. The state of stress at a point on an element is shown in figure A. The same state of stress is shown in another coordinate system in figure B. The components tau xx, tau yy, tau xy are given by, so it's a problem of rotation of the plane. Mohr circle for the stressed element shown in figure A. This point represents the stress P, which is tensile, and in opposite negative direction this point represents P, compressive. Now tau xx is in direction if we rotate it by 45 degree. So on Mohr circle we rotate 2 into 45, that is 90 degree. So it is vertically down. We know that the normal stress vertically down from the origin is 0. So tau xx will be 0, and tau xy would be the maximum stress, and which is the radius of the circle, which is nothing but P. So we have found out tau xs and tau xy. Now we have to find tau yy. Tau yy is at a direction 45 degrees anti-clockwise. So we rotate it 90 degrees anti-clockwise, and which is this direction, and here tau yy is again 0, since the normal stress is 0 at this point, which is vertically up the origin. So we can write tau xx, tau yy, and tau xy is equal to 0, 0, and P. Let's solve this problem analytically. We know that normal stress at a plane inclined at theta is given by sigma x cos square theta plus sigma y sin square theta, and the shear stress inclined at theta degrees is given by minus 1 by 2 sigma x minus sigma y sin 2 theta. Now tau xx is inclined at minus 45 degrees. So we put value of theta minus 45 to get tau xx. So we get sigma x is p, cos square minus 45 will be 1 by 2, and sigma y is minus p, sin square 45 will be 1 by 2, which gives 0. And tau xy will be minus 1 by 2 sigma x p, sigma y minus p, sin 2 theta is sin minus 90. So we get value here minus 1 by 2, 2p into minus 1, which gives value p. So we have found out tau xx, tau xy as 0 and p. Tau yy is inclined at plus 45 degree. So putting theta is equal to plus 45, we will get tau yy in the above equation. So tau yy is p cos square 45 minus p sin square 45, which is 0. So the answer is tau xx, tau yy, tau xy is equal to 0, 0 and p. The next question is the state of stress at a point P in a two-dimensional loading is such that the Mohr's circle is point located at 175 megapascals on the positive normal stress axis to determine maximum and minimum principal stresses. On the Mohr's circle, the maximum and minimum principal stress are obtained by the intersection points of the x-axis and the circle. It's given that the Mohr circle is just a point at plus 175. So here the intersection point are sigma 1 and sigma 2. Both will also be equal to plus 175 MPa. Analytically, we know that sigma 1 and sigma 2 are given by 1 by 2 sigma x plus sigma y plus minus r. R is the radius of the Mohr circle. So sigma 1 sigma 2 will be 1 by 2, 175 plus 175 plus minus 0, since radius of the Mohr circle is 0 as it is a point. So we get sigma 1 sigma 2 is equal to 175 MPa. This question is also based on the past question. The Mohr circle is a point located at 175 megapascals on the positive normal stress axis. In this problem, we have to determine the direction of maximum and minimum principal stresses at point P. Direction of maximum and minimum principal stresses are the direction of planes carrying the maximum and minimum stress. But in this particular case, the planes in all directions carry the equal stress of 175. So all the planes are principal planes and direction is in all direction. Analytically, we know that direction of principal plane is given by theta p, then tan theta p is equal to twice tau upon sigma x minus sigma y. In this case, tau is 0 and sigma x and sigma y are 175 each. So we get an answer of 0 by 0. This is indeterminate form. So the direction of principal stress are not in any particular direction. It cannot be ascertained mathematically. So we can say all directions is the answer. This is another gate question. A two-dimensional fluid element rotates like a rigid body. At a point within the element, the pressure is 1 unit. Radius of the Mohr circle characterizing the state of stress at the point is. So we have to find the radius of the Mohr circle. From Pascal's law, the pressure would be equal in all directions. So sigma x and sigma y both will be of equal magnitude. The pressure acts in radial direction, so there will not be any shear stress also. So sigma x and sigma y being of equal magnitude and absence of any shear stress makes the Mohr circle a point. So the radius of the Mohr circle would be 0. Mohr circle is drawn taking sigma x from the origin on x-axis and then sigma y from the origin on the x-axis again, and taking tau vertically downward on y-axis and tau here also, and we get the midpoint of sigma x and sigma y as center of the circle. In this particular case, since sigma x is p, even sigma y is also p, so these 2 points coincide. Since tau xy is also 0, there is no vertical line here, so the Mohr circle is just a point. The figure shows the state of stress at certain point in a stressed body. The magnitudes of normal stresses in x and y directions are 100 megapascals and 20 megapascals respectively. The radius of Mohr circle is to be determined. Sigma x is plus 100 and sigma y, since it is compressive, is minus 20 MPa. So the radius of the circle, which is the tau max, will be sigma 1 minus sigma 2 by 2, that is 100 minus 20 by 2, that is 100 plus 20 by 2. So the Mohr circle radius would be 60. So this was a very straight question asked in the gate. The next question is, the Mohr circle of plane stress for a point in a body is shown below in the figure. The design is to be done on the basis of the maximum shear stress theory for yielding. Then yielding will just begin if the designers choose a ductile material whose yield strength is. So we have to find tau max and then the yield strength. Tau max on the Mohr circle, we know that is equal to radius of the Mohr circle. So radius is minus 10 plus 100 by 2, which gives a value 45 MPa. Now we also know that tau max is equal to sigma yt by 2, where sigma yt is the yield strength of the material. So if we take sigma yt is equal to twice the tau max, the material will start yielding. So the answer is 2 into 45 is equal to plus minus 90 MPa. Next problem is, the state of plane stress at a point is given by sigma x is equal to minus 200 megapascals, sigma y is equal to 100 megapascals, and tau is equal to 100 megapascals. The maximum shear stress in megapascals is. A circle for the problem can be drawn from the origin. We draw sigma x, since it is negative, in opposite direction, that is minus x direction, 200 MPa, and sigma y 100 in positive x direction, and then tau xy 100 like this, and we draw a circle from the center of the sigma y and sigma x. So the value of maximum shear stress is the radius, and radius comes 180 MPa. And analytically, tau max is equal to root sigma x minus sigma y by 2 whole square plus tau xy whole square. So putting values for sigma x, we have minus 200 minus 100 by 2 whole square plus 100 square. Solving this, it gives a value of 180.28 MPa.